Our next speaker is somebody that has a rich experience in history in natural language processing and voice and robotics. I'm very pleased to bring up Chiori Hori with Mitsubishi. Chiori, come on up. Mitsubishi Research Labs, excuse me. Let's get that right. Okay, are you mic'd up? You ready?
Yes.
Okay,
Yes.
Chiori, take it away. Thank you.
Thank you. So, hello, everybody. So, I'm from Mitsubishi. I have worked on speech recognition for 20 years, very surprisingly. So today, I sneak out from my laboratory to introduce the history of speech recognition and the cutting edge of spoken dialogue system. And now, goosebump event is we are going to recognize what's going on surrounding us using computer vision technologies. Okay, so we have a speech interface, as you know, smartphone, car navigation, and smart home. And in the near future, we would like to collaborate with robots. We would like to make a spoken dialogue system for that technology. Now we are working hard. Let me look back the history of speech recognition. Actually, New Jersey is a special place. AT&T Research Laboratory is still located in here. Professor Flanagan studied the speech recognition research, and 40 years passed. So every 10 years, famous researchers are called as a liar, but now you have a technology in your hands. So at the beginning, our technology is only for isolated speech recognition. So just number can be recognized. And then, so we can recognize much more longer sentences, but still, we just recognize word spotting way, Boston like that. And after that, of course, we had a continuous speech recognition. We can recognize much more longer phrases, rule-based understanding. We were able to do that. In 2002, actually, in the field of natural language processing, Watson-like a question answering system was very popular. Factoid named entity was extracted based on classifiers like a support vector machine. If you asked the system which country won the World Cup, actually the system had multiple hypotheses in the database. So they are trying to confirm more information is required. Okay, what kind of World Cup or when? And finally, the system can recognize the answers, and Brazil won the World Cup in 2002. So people want to combine the speech technologies and the question answering, but unfortunately, the speech recognition was really poor. The vocabulary size is only 2,000, and we were not able to, whatever you want to speak. And after that, AT&T introduced weighted finite state transducer. Dr. Morley proposed that one. It worked very good. But still, real-time system was not be able to realize. This is because the vocabulary size, we would like to recognize 2 million words in real time. And after that, we introduced the on-the-fly technology. And finally, we have the speech recognition, which can recognize 2 million words. Now, when you would like to make the dialogue system, how to build that one? So this is a database. So this is a hotel reservation conversation. So of course, we have roles here, agent and client. So agent said, hello. So now this is a New York City hotel. May I help you? I would like to make a reservation. This type of discussion is ongoing. So of course, human beings exchange information using natural language. But system needs to understand the concept. Otherwise, there are many paraphrases. The most difficult part is how to recognize what they meant. So after that, we are trying to translate from the natural language to the concept text. And then we needed to think about the context. So what types of things are discussed in the dialogues. And finally, we can predict the system next action. But still, that is a system symbols. We needed to generate the natural language. So we needed to translate back from the symbols to natural language. So after that, we need to make a graph like that. It is very, very painful task to generate such a graph to make a dialogue systems. So then we need to think about the difficulties in the natural language. So different expressions, but same concept, like open question and yes, no questions, but the same contents in there, like what kind of room would you like to stay? This is open questions, but yes, no question, like do you have any particular room type in mind? So actually, the user's response is the same. So in that case, the system needs to understand this is the same concept. And the second problem is same expressions, but different concept. So user says thank you, but actually there are multiple meanings in there. So in appreciation, so the system needs to say you are welcome. But acceptance, system needs to take a next action. And greetings, so in that case, have a nice day, that is enough. To realize this if-then rule-based one or finite state automaton, so we need to build a nice platform to absorb all frameworks to represent the dialogues. So weighted finite state transducer is very good to absorb all formats. And the most important things, we need to make a system to understand with conditional concept. So it means that we need to think about the context of the dialogue, and in the end, we need to decide the actions. This framework will let us to build the system separately, developers by developers. Means that if someone needs to add the new vocabularies to the dictionary, so speech recognition layers separately to build the dictionaries. And if someone wants to make a new dialogue systems, so just to make the graphs by themselves separately from the speech recognition. Of course, we need the back-end system, like a flight ticket booking system or any other things. So everybody can work on their own task, and finally, we combine everything into one network and to search what's the next action. That's the concept. And we built the system for Asimo. Have you ever heard about the Asimo? That is a small humanoid robot. Japanese people are kind of fantasized by human robots. And the robot visited Carnegie Mellon University in 2004. And at that time, I worked for the Carnegie Mellon University, and the hall was filled with people, and I was in the last line of the audiences. I looked at the robot. He danced. Actually, he danced, he walked, and he played soccer with President Obama. Unfortunately, he was not able to speak any words or have a conversation with us. I decided, okay, it's high time to build the dialogue system. And 10 years passed. Actually, I implemented the weighted finite state transducer-based dialogue system for him. He can speak English, Japanese, Chinese, and also the dialogue understanding is based on language-independent network. So it means that Asimo can translate, handle spoken dialogue between 3 languages. And after that, so we are thinking about that this is a cooking system. If you'd like to make a cooking system, on the web, we have tons of recipes. Actually, the recipe has the same format. Like, first of all, the page say that, okay, so actually the gradient. They listed the gradient and also the amount of gradients in the first line. And then they speak about how to cook the ingredients step by step. So if you can pass the data on the web, actually we can make the dialog systems. Of course, the dialog itself is very naive way, just to let the users interact with the system. Okay, how many eggs? So in that case, the system just retrieve the number of eggs in the database, and the steps, how to cut the tomato. So in that case, the system try to find the data in the table, so how to cut. So we can make the rule-based system by manually. So, but this slide shows that how difficult to build the human-like dialogue. The first one is rule-based model that is actually tour guide system. If we are trying to make the system using handcrafted rules, that is very simple question answering. But the middle and the last graph shows that. So the first one, green one, shows that guide actions simulator. So means that 100 users visited our laboratory to discuss about one-day trip, and 3 guys to instruct where they need to go. And the third blue colors graph shows that the hotel reservations, the difference between 2 graphs. Okay, so travel planning at the beginning, users don't have any ideas. So that's the reason why left side is very dense. But in the last graph, hotel reservation, actually the first question is very simple. Okay, king bedroom, like a very simple, but after all, they needed to decide many details. That's the reason why the last layer is very dense. So if we are trying to make a human-like behavior system, suddenly the network looks like that. The difficulty of the dialog system is actually how to understand users' spontaneous input. That aspect is the most difficult part. If secretly, so human being is an agent, just accept system's input. That is not difficult. This is because, date, number of people, whatever, everything is clearly defined for the system, and it's just the system speak to the humans. Human can be a kind of, very nice way to absorb system's input, not so difficult. So if customers behave very freely and spontaneously, that most difficult part is that spontaneity. Okay, so you can see it is very difficult to construct the dialog system using our hands. So that's the reason why we would like to build the system using statistical models. In our cases, we use the Enneagram-based concept tag symbols are modeled in that. So of course, the problematic thing is, as I showed the table, we need the data first. And after that, we need to translate the natural language to the symbols, concept tags. That is too much expensive. So now, in 2014, deep neural network was applied to sequence. Google researchers proposed one method to generate source sentences to target sentences in machine translation. Actually, that changed everything. Right now, speech recognition has been already changed. This is because before, we needed to transcribe speech. And then we needed to transcribe the phoneme sequence and dictionary. Everything is very expensive by humans, created by humans. But now, sequence-to-sequence model, if we input the signals into the system, actually character is output. So it means that we don't need any extra additional things to make the dictionaries or phoneme sequence labeled data set that will be gone. And that technology is applied to Dialog as well. So we organized the Dialog Technology Challenge that is for academics. So students or industry side come together to tackle with one shared data set. In our cases, DSTC6. Twitter data is collected by participants, and we collected the user customer services using that data. So people complain about something to the Twitter, and the customer service try to take care of that issues. Those dialogue is corrected, text-based one, and new end-to-end dialogue technology is applied. Deep neural network is applied to that one. We get 21 systems here. The left one shows that human beings' behavior, and the right one, so other graph shows that the system's output. At the beginning, I thought that we generated in grammatical sentences. But actually, sentence is very nice. And when we compare the performance between the systems and humans, actually not so bad. So the ratio of the rating 5 is a little bit smaller than the systems, but others are almost comparable. Seems like end-to-end dialogue systems will be available soon if you have the data. And here is an example. The first table shows that the problem is for the flight cancel. So the users complain about how difficult they stayed at the airport. And the best system is very synthesized with users' feeling and try to solve the problems. This is automatically generated from the systems, very surprisingly. And the worst sentences like, even the users are very uncomfortable, but the system responds, I'm happy to hear that. That is a problematic thing. But that problem has been solved. If I collected double size of the training data, suddenly the system recognizes the sentiment. Okay, this is uncomfortable. So we cannot say, happy to hear that. And the system can generate much nicer sentences. If you collect more data, we can generate more nicer sentences. Okay, let me move on the multimodal aspect. So next generation, we have a very nice speech recognition in our hands. And the spoken dialogue system gradually getting better. Rule-based one or statistical-based one, so we can build a very nice one, gradually, step by step. And next one could be, so human to robot. So look at this figure. So human to robot, look at one scene. So this is two robots in front of them. They are discussing about something on it. And the user said, okay, that's a cool robot. In his mind, actually round robot is in there. But for the robot, actually, they can recognize RGB and flow, but that is only for 010001. Human beings cannot exchange information using such numbers. So those of information should be translated into the natural language. So semantically, we need to understand what's going on surrounding the robots. So actually, if we input the video features into the system, deep neural network generates sentences to describe scenes ongoing here. And after that, okay, the system said two robots in here. One is humanoid, the other one is round-shaped, And okay, now robot has a knowledge. So after that, the context is, that's a cool robot he mentioned. Okay, there are two robots. The response should be, which one? So round one or humanoid one, this type of responses should be generated. Okay, now in the field of AI, actually not only for speech, not only for dialogue, not only for the natural language processing, and now computer vision features will be introduced. And when we recognize things ongoing, actually we need to understand the conditions, so concept here. And we are trying to generate a system by combining text and audio and video features. If you have more sensed information, of course we can add such information to recognize things ongoing. So here is a kind of history of the information retrieval for images. So of course, since 1990, people input the query into the retrieval system and trying to get the appropriate pictures. And after that, not only isolated words, queries can be phrases. And then, so people start to generate sentences using static image features. So now we can recognize static image. And also, we can describe in the videos. The framework is the same. We are trying to extract the image features and audio features and the flow features here to try to generate word sequence. Look at this one. Actually, computer vision guys don't care about audio features at all before. But in my case, my background is audio processing, so I would like to add more important thing. This is because in real life, something happened. Of course, we have sounds and visual information all together. So look at here. So our girl is standing on a hill. If object recognition system can recognize hill and a girl, they can generate these sentences. After that, so our girl is jumping. That is a kind of motion. So in that case, we need to recognize flow. And then, so our girl is looking at airplanes flying overhead. In this case, we can see that airplane before, but now disappeared. But still, we have sounds and airplanes. So in that case, we need to generate that sentence. Our girl is listening to the airplane, so we need an audio feature. So now we are trying to combine multimodal features into one system. So of course, multimodal fusion, that is a very important field, research field. There are many techniques was proposed, but so recently deep neural network is shown up. Everything is drastically changed. I think as far as I know, how to fuse the multimodal features and deep neural network, we firstly introduced here. So this is actually, you can see that blue box shows that one of the multimodal features, like audio features, and red one shows that visual features, different features will be combined together. So Microsoft guys introduced the attentional model for this video descriptions. And then we start to think about, okay, temporal attention is not enough to think about the multimodal fusion. We decided, okay, please add the weight between modalities. So sometimes audio features needs to be weighted, sometimes visual features needs to be weighted. And we tested the performance using the shared training data. So you can realize that each video clip has descriptions, 40 descriptions or 20 descriptions. So the people hired Amazon Mechanical Turk to describe the videos, and we trained the model using the video features, audio features, and description text. So of course, actually the video description data itself is not enough. Now we need to have a technique to characterize the features in the videos, even the data set is small. In that case, we have another pre-trained model that has been already pre-trained using tons of data, like ImageNet. So we have tons of data for a static image, trained models. They can recognize object very accurately. And of course, another model is action recognition models. We use that models to extract features. So, and also, actually, Google has a very nice system right now, audio event detection. Huge data is trained to predict the 150 classes. And we use those models to extract features to combine everything into one. And here is an example. Let me show one example. Okay, can you recognize what's going on? If we just use the image recognition model, so a monkey is running, that sentence is coming out from the systems. And when we combine the action recognition model, a dog is playing. When we add the attention, modality attention into two systems, two models, a monkey is playing a dog's tail. Much more accurate sentence is coming out.
Off of the stem end, just to give our fingernail a place to pull back all of the onion skin. Off of the
Okay, can you hear that sound of peeling? So when we just use object recognition model, mine is slicing a potato. And when we use action model, mine is cutting an onion. Now, we can combine the audio features and the modality attention is attached to predict the sentences. Actually, mine is peeling an onion, much more accurate sentences coming out. So do you know which instrument is he playing? Can you guess? So this is not guitar. Actually, even Amazon Mechanical Turk has annotated guitar, but this is violin. So the first sentence, object recognition, is strongly recognized microphone. That's the reason why a man is singing. So actually, he is not singing here. And the second one is we just combine everything equally without no attention between modalities. A man is playing a guitar. But when we add the modality attention to generate sentences, here a man is playing violin. Now accurately recognize violin here. So I think the most important thing is we need multimodality and to pay attention between modalities case by case. And the most interesting thing is if you equally combine all features, actually nobody knows about which model generates which word. But if you have the weight between the modalities, suddenly we can know which word comes from which model. So it means that much more precise analysis can be done using multimodal attention mechanism. And then now I would like to introduce new activity. So I collaborate with Georgia Tech. They're working on the VQA, visual QA. So people try to discuss about the static image. So, but that is only for static image. So which color of the beard or what is beard like? And then after that, they're working on the visual dialogue, means that much longer, discussion needs to be done to clarify in the static image. And after that, we are going to make a system for the videos. So if you are going to install the surveillance cameras, 2,000 surveillance cameras, can you recognize what's going on? Human can find the incident? No. So we need to make the systems to find something ongoing. And humans would like to ask questions to the systems. If systems respond to extract answers from the video, that is very nice. And we collected the data for chalets, that is actually human actions recognition data sets. And people discuss about what is he doing. where is he going? Like this type of questions were collected. And now we can introduce the visual, like audio-visual scene-aware dialogue. This is for the many aspects, like combining multimodal features and also question. And the context of dialogue is input into the system, and the system is trying to figure out what should be responded to users. And then, so of course, industry side, people want to clarify this type of technology can be applied to which part. So you can see that car navigation. So bounding box system let us know where is the pedestrians, bicycles, but the system just make the bounding box, that cannot help us. So natural language processing system, dialogue system let us know, okay, two bicycle coming by right side and the police car is coming backward, like most of the information will be given in natural language. That is very helpful, very intuitively grab the information. And of course, as I told you, the surveillance cameras, of course, surveillance cameras let us know the incidents. And in the future, robotics. So people to discuss about that things, we have to do. The system said that please cut the yellow line, but the humans are trying to cut the red line. So maybe the system will let us know what we should do. So now let me introduce the next challenge, Dialog System Challenge, Technology Challenge 7. So Microsoft is organizing a sentence generation for the dialogues. IBM is organizing the challenge for the sentence selection. In our case is audio-visual scene-aware dialogues. If you guys are interested in to come, so please join us. Thank you.